Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face Trending List, published on September 22nd, 2025, which was about 3 days ago. The key result is a new privacy notion called B-privacy that ties privacy to the cost of bribery, and a noised tally method that raises B-privacy by a geometric mean factor of 4.1 times for proposals where at least 5 voters are needed to flip the outcome. The paper is titled B-privacy, defining and enforcing privacy in weighted voting. And the implications for blockchain governance are quite significant. Beyond that, this paper shows tallies can leak votes at scale, with attacks recovering at least one voter on 81.0% of proposals and all votes on 29.2%, formalizes a Bayesian bribery game, and finds whale concentration limits any privacy gains while winner-only and noise tallies still improve bribery costs overall. Alright, the previous segment highlighted why publishing exact tallies leaks votes. Table 1 summarizes 4 tally algorithms and what each reveals. Winner only reports just the winning choice, raw tally reports total weight for every choice, noise tally adds random noise to each choice total, and full disclosure releases the entire transcript. The noised option matters because the added randomness raises bribery costs while still conveying approximate outcomes. Alright, the previous table contrasted tally disclosure choices. Algorithm 1 now presents the unified attack that extracts individual ballots from a raw weighted tally. The procedure first applies a whale attack, which assigns any voter heavier than the second highest tally to the winner and subtracts that weight. It then runs a meet in the middle subset sum search per remaining voter, and when exactly one choice fits, it fixes that vote and updates tallies, so complexity stays practical for about 45 voters. Well, the previous algorithm showed how ballots could be extracted efficiently. Figure 1 shows a scatter across DAOs, with mean ballots leaked on the x-axis and mean voting weight leaked on the y-axis. The trend concentrates many points high on weight leakage, which means whales get exposed even when few individual ballots are revealed. The highlighted contrast is striking. Arbitrum sits with heavy weight leakage while Aavegotchi leaks far less, and Balancer nears complete exposure, so concentration of voting weight dominates privacy outcomes. Alright, the previous figure emphasized how weight concentration drives leakage risk. Figure 3 formalizes the bribery game that defines B-privacy. The inputs include voter weights, utility distributions for the no option, and a chosen tally algorithm, while the players are many voters and one adversary whose goal is a yes outcome. The sequence is simple yet strategic. The adversary commits bribe amounts and payment conditions. Voters choose simultaneously to maximize expected utility, the tally reveals outcome information, and payments follow under Bayesian-Nash equilibrium. So, the previous figure defined the bribery game. Figure 4 shows how adding 10% tally perturbation with 95% frequency slashes attack effectiveness. Points shift left and down, because the adapted whale attack loses certainty, and the subset sum reconstruction breaks under noise. The light lines connect raw tallies to noised outcomes, which illustrates the reduction per DAO. The legend clarifies that dark dots are noise tallies, and light dots are raw tallies. Alright, the previous figure showed noise reducing attack power. Figure 6 shows relative B-privacy rising as tally perturbation increases, with lines grouped by minimum decisive coalition size from Aavegotchi proposals. The y-axis uses a log scale, so straight-looking climbs reflect large multiplicative gains. Larger minimum decisive coalition cohorts achieve higher B-privacy at any fixed perturbation, and gains plateau around 10% noise, which indicates diminishing returns beyond that point. So Figure 6 showed gains from adding noise. Figure 8 compares adversarial success versus total bribe budget across 3 disclosure choices: full disclosure, 10% tally perturbation, and winner only. The curves shift right as disclosure decreases, which means higher budgets are needed to hit the same success. The dashed red line marks the target P equals 0.9, and bold lines mark the cheapest strategy per panel, which closely matches simple heuristics. Alright, 2 takeaways stand out. B. Privacy reframes privacy as the bribery budget an attacker must spend, and modest tally noise with winner correction, meaning about 10% perturbation, meaningfully raises that budget. The broader implication is clear. Governance needs disclosure policies and voter decentralization, since whale concentration caps any protection. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.